Let's take a look at a new topic. We've been working on using the distributive property and combining like terms and that sort of thing, and now we're going to turn our attention to something that I'm hoping you've heard some of these vocabulary words before and that you're somewhat familiar with this, but we'll practice this and make sure we're aware of how this goes. So this is section 2.4, and the I can statement for today is I can find the greatest common factor. So greatest common factor. And because this is kind of a long phrase and because we use it so often, we use a short little abbreviation for it. We call this the GCF. So if somebody says greatest common factor or GCF, they're talking about the same thing. So as the warm-up, I've got three different questions here. First one is, which of the four basic operations, so remember the four basic operations are add, subtract, multiply, and divide, which of the four basic operations is represented in the expression 5xy squared? So if you remember, we used a lot of implied multiplication. Multiplication is the only operation that we can write without using a symbol. So this literally means 5 times x times y squared, and remember y squared means we use the y twice. There are two y's in that multiplication problem, so it's multiplication. So of those four basic operations, the one that we're indicating here is multiplication. And then I want you to take a look down here. We're talking about multiplication problems, but we want to be aware of the vocabulary that we use with these. That's really important to know the vocabulary. So what are the parts of a multiplication problem called, and what is the answer to a multiplication problem called? So again, hopefully you've heard of these before. The parts of a multiplication problem are called the factors. And the answer to a multiplication problem, or we might refer to the multiplication problem itself, we call that the product. Okay, so we've got factors that make up the product. So the factors here are 5 and x and y, and the product is 5xy squared if we write it in simplified form. So this leads us to something that's really important, a key idea, and that is that a lot of what we learn in math is about learning how to do something and then learning how to undo that thing, so reverse that process or whatever it happens to be. So we're really good at multiplying numbers and expressions to find their product. That's what we've been doing when we were using the distributive property and things like that. So we're really good at taking the factors and multiplying them together to figure out what the product is. Now we're going to learn how to take a product and find its factors. So we're going to do the opposite. We took factors and figured out what the product is, and now we're going to take the product and figure out what its factors were. And the most basic type of factoring is called prime factorization. And hopefully you've heard that word prime before. If not, we'll remind you of what it is. Okay, so you probably learned how to do this using something called a factor tree. And if not, they're pretty easy to work with. But we do need to remember what a prime number is. A prime number is one that is only divisible by 1 and itself. So the only things that go into that number are 1 and itself. So for example, 17 is prime. The number 16 is not prime. 17 is prime because that would just be 1 times 17. That's the only way to make that a multiplication problem. There are lots of ways to factor or to break 16 down. 16 could be 4 times 4. It could be 2 times 8. It could be a bunch of different things. So prime is a number that is only divisible by 1 and itself. So let's take a look at example 1. Now you're going to need to know how to do this in order to do today's assignment, but these types of problems won't be on the assignment, but these will really be helpful. So let's do a couple problems here as a review. So it says find the prime factors of the following numbers. So here's what we do, and this is, I'll do a factor tree for a couple of these and we'll see how this goes. So what we do is we kind of break this down and we figure out anything that goes into 60. So any numbers that multiply to be 60. So we're going to take this number right here, we're going to take this product and we're going to break it down into any two of the factors that would go into that. So we could say, well, 60, gosh, most people would probably think 6 and 10. Okay, now 6 is not prime because we can break that down a little bit further. So we're going to take this and we're going to break it down into two factors. 2 goes in there 3 times. And 10 we can break that down. That goes, let's see, 2 times 5. Now 2, the only thing that go into 2 are 1 and 2. The only thing that goes into 3 is 1 and 3. So those are both prime numbers. And 5 is also prime. So what we've done here is we've broken this down all the way. And then when we write this as being prime factorized, if we want to use that phrase, it's usually best to kind of write these in order. So I'm going to write 2 times 2 times 3 times 5. So 2 times 2 would be 4. 4 times 3 would be 12, and 12 times 5 would be 60. So even if we didn't do the 10 times 6, if we broke it down another way and said we did 2 and 30, and then broke down the 30 and so forth, you're going to end up at the same place. So these are all of the prime factors of 60. Let's take a look at 45. Let's see, most people probably would think 5 and 9. 9 is 3 and 3. 3 times 3 makes 9. 5 doesn't break down anymore. So again, I'm going to write them in this order. I'm going to write them from least to greatest. So 3 times 3 times 5. And that right there would be the prime factorization. Now, we don't have to do it this way. If you can kind of think your way to the answer, that would be fine. And if you use a different set of numbers to break it down to begin with, that would be okay. Now, let's say, for instance, maybe for some reason you thought 3 goes in there 15 times. Totally okay. 15 would be 3 times 5, and you'll notice that we still end up with the same thing. We end up with 3 times 3 times 5. You'll notice that each one of these branches stops when we get to a prime number. That's how we know we stop at the end there. And we didn't stop at 15 because 15 is not prime. We can break that down. So let's do 56. Now, you may have a number that pops into your mind or a couple numbers that multiply to be 56. If you do, that's great. I'm going to do this. I'm going to say, well, that's an even number, so I know 2 goes into it. If I do 56 divided by 2, 50 divided by 2 would be 25. So it's got to be a little bit bigger than that. It's actually 28. And then I know this is still even, so 2 goes in there. Goes in 14 times actually. That's even, so I know 2 goes in there, and it goes in 7 times. So we've actually got 2 times 2 times 2 times 7. So you want to be really good at prime factorization, and you want to be pretty good at it. And again, each one of those branches stops when we get to a prime number. Let's take a look at 37. 37 is not even, so 2 doesn't go into it. 3 doesn't go into it. 4 doesn't go into it. In fact, there's not an even number that's going to go into that. 5 won't. 7 won't. Well, you can try every number you want. The only number that will go into that is 1. So what that means is 37 is a prime number. It only has those two factors, 1 and 37. So 37 would be prime. If you did have to factor it, the only way to factor that would be just 1 times 37. Okay? But usually we just indicate something like that by saying that it's prime. Okay, now let's talk about, now that we know, we've kind of reviewed and reminded ourselves how prime factorization works. If you do the factor tree, you can get there. If you've got some other ways to do it, that would be totally fine. But now we're going to talk about what the greatest common factor is. So greatest common factor. If you think about what the word common means it happens a lot. Or it's, when we say it's common, it might happen in a couple different places, and that's kind of what it means in this setting right here. So the greatest common factor of two numbers or two terms, that's what we're going to work with a lot of the times, is the greatest number that divides into both numbers evenly. In other words, it's got to be a factor of both of those numbers. So greatest common factors are used all the time in math, especially when we're simplifying fractions and other expressions. Factoring is going to be used a lot this year and in years to come. Okay, so I want you to write this down. I want you to write this down in capitals. Factoring will never go away. The better you are at factoring, the better off you're going to be in the long run. We use factoring all the time. It's got a lot of different applications. So we're going to work on a very basic type of factoring. It's finding the greatest common factor, but that really is the tool that we use most often when we're factoring. So let's talk about how to find the GCF of two terms. So to find the GCF, the greatest common factor of two terms, we list the factors of each term, kind of like we did up above, and then we include only factors that appear in both lists to make the GCF, to make the greatest common factor. So let me say that again. To find the greatest common factor of two terms, we list the factors of each term, and then we include only the factors that appear in both lists to make the GCF. So let me show you how that works. And so here are the instructions, and here are the problems that we're going to take a look at. Show your thinking to find the GCF of the numbers for each problem, then write and circle the GCF. So here's what we're going to do. Now you'll notice we've got 60 and 45. Now you may be able to think of a number that goes in both of those evenly, but we kind of did a little bit of extra work here. Take a look at what we've got right here. We've got 60 and 40. So we already have a list of the prime factors for each of those. So 60 is 2 times 2 times 3 times 5. 45 is 3 times 3 times 5. Now remember, we're only going to include factors that appear in both lists to make the GCF. So there's a 3 here and a 3 there, there's a 5 here and a 5 there. So I've got a 3 and a 5 here and a 3 and a 5 there. So that means the GCF is 3 times 5, or in other words, it's 15, and that's it, we're done. Here's the answer. Now, we got a little bit of help because we had done that work earlier with 60 and 45, but let's do 30 and 24. We haven't done this. Now, if you need to do a factor tree for each one of these, that's totally okay. You can write one off to the side. You could do 30 over here and 24 over here, something like that, and then we'll say, let's see, that would be 3 times 10 and then 2 times 5. So we've got, and again, I like to write them in order, so I'm going to do 2 times 3 times 5. Let's see, we'll try 4 and 6, 2 and 2. Let's see, 2 times 3, so this would be 2, 2, 2, and 3. Okay, so if you need to do a factor tree, that's totally okay. I'm going to kind of wall this off so we can see where this problem and the work starts and stops. Now we're only going to include factors that occur in both of the lists. So notice that we've got a 2 in both of them, and we've got a 3 in both of them, but not a 5. And notice that we've got 3 2's here, but we only have 1 2 over here. So one way we can do this is we'll say, okay, we've got a 2 in common, and we've got a 3 in common. So that means we've got a 2 times 3 as a greatest common factor. That's the only thing that's common to both lists. So that means the answer on this one is 6. So you may have been able to look at some numbers like this. These are part of your 6 times tables, if you want to think of it that way. 6 is the biggest number that goes into both of those evenly. 12 goes into this one. That's a bigger number than 6, but 12 doesn't go in there. This is a good way to identify what it is. Now, again, if you need a factor tree to do these problems, go right ahead. I'm not going to be using factor trees from now on. It takes up a lot of space, but if you need to again, write one off to the side, that'd be totally okay. So here's what I'm going to do. I'm going to factor 16. So, and I'm going to do it this way. 2 goes in there 8 times, 2 goes into 8 4 times, and 2 goes into 4 twice. So if you check here and see, this would be 2 times 2 is 4, times 2 is 8, times 2 is 16. Or you could think 16 is 4 times 4, 2 times 2 is 4, and 2 times 2 is 4. So there are the 2 4s. Okay, so I've got my list for 16. Let's do 56. 56 would be 8 and 8 times 7. And 8 is 2 times 2 times 2, and then times the 7. Again, if you need a factor tree to confirm that, go right ahead. 32 is twice as much as 16. So I'm going to do this. I'm going to write down those 4 2's that make 16, and then if I double that, that's going to make 32. Again, if you have a tough time following that, you can write a factor tree for each one of those, and you'll end up with these. Now, let's take a look. I've got 4 2's here, 3 2's here, and 5 2's right here. This one has a 7, but these other ones don't have 7's. Now, what we set up here is to find the greatest common factor of 2 terms, we list the factors of each term and then include only factors that appear in both lists. Well, if we've got 3 terms that we're trying to find the GCF for, it's got to appear in all of those lists. So take a look here. This one has 3 2's, 4, and 5. So we are limited by this one right here. We've got 3 2's in each one of these. So the greatest common factor is 2 times 2 times 2, so the greatest common factor is 8. Now, if you can look at these numbers and say, gosh, the biggest number that goes into 16 and 56 and 32 would be 8. If you can figure that out from scratch, that's totally okay. I'm fine with that. But again, if you need to use a factor tree and list them out like that, that's just fine. So let's take a look at this one right here. Let's see if we can figure this one out and take a good guess at it without doing a factor tree. 28, 42, and 56. I'm hoping those numbers look kind of familiar because you've got your multiplication tables memorized from elementary school. Those are all in the multiplication list for 7. 7 goes into all of those, but they're also all even. So 7 would go into each one and 2 would go into each one of them. So if 2 goes in there and 7 goes in there, here's our guess. Greatest common factor would be 14. Now, if we want to check that, 2 times 2 times 7, 4 times 7 would be 28. This would be 6 times 7, so that would be 2 times 3 times 7. And this would be 8 times 7. We did 56 just a second ago, so that's going to be 2 times 2 times 2 times 7. So take a look here. There's a 2 and a 7. There's a 2 and a 7. Whoops, let me make that look a little bit better. Okay, and there's a 2 and a 7. So 2 times 7, greatest common factor is 14. All right, let's see if we can speed this up just a little bit. Take a look at this one right here. 15, 35, and 55. You be thinking, I'm going to show a little bit of work here. Not too hard to prime factorize each one of those. You'll notice the only thing in common with each one of those is a 5. 5 is the biggest thing that goes into those evenly. Now this one looks a little bit tricky. You'll notice that we've got the number 22, 37, and 41. Now 37 and 41, those are not the nicest numbers. This would be 2 times 11, but 37 is actually a prime number, so that means that that would be 1 times 37, and 41 is also a prime number, so that would be 1 times 41. So you'll notice that they really don't have anything in common, but keep this in mind. You can always put a 1 as part of a multiplication problem. So now you'll notice that each one of these has a 1. So in other words, the biggest number that goes into all 3 of those would be 1. That's the greatest common factor. That doesn't happen very often, but that's what we end up with right there. Okay, let's take a look at this one. And I'm going to go ahead and break these down and write these as prime factors. This would be 2 times 9, which would be 3 times 3. And then I'm going to write down 3 b's. 6 is 2 times 3. And I'm going to write down 2 b's. So let's take a look at what's common. We've got a 2 and a 3. Got that part taken care of. We've got 3 b's over here, and we've got 2 b's over here. Well, this one has 2 b's and this one has 3, so the most that would be common to both lists would be 2 b's. So I've got a 2 times a 3 times a b times a b, so that's going to be 6, and then again the easiest way to write b times b would be b squared. So 6b squared is the biggest thing that would go into both of those evenly. That's the greatest common factor for those terms right there. Let's take a look at this one. Let's see, this would be 2 times 2 times 5. 4 times 5 is 20, okay? And then AB, and this again, that would be 4 times 4. We did 16 earlier, so that would be 2 times 2 is 4, 2 times 2 is 4, and then we've got an A. Gosh, we've got all these 2's right here, but this one only has 2 2's, okay, so we definitely have those in common. And then we've got an A and a B here, but we've only got an A over there. So what we have here is 2 2's and an A that's common to both of those, so that's going to be 4A as our greatest common factor. And then the last one here, and then we'll give you time to work on your assignment, and you can practice this stuff yourself. Take a look at 22 and 4. Think about the biggest number that would go into both of those evenly. Well, since they're both even, we know 2 would go in there. 4 goes in here, but 4 won't go into 22. So 2 is the biggest number that goes in there. And then take a look at the x and y here and x squared here. That means there's 2 x's over here. But since there's only 1 there, that kind of limits us. So the biggest factor as far as variables go would just be the x, and then clearly we don't have a y over there. So that would be the answer on that one. And the thing I want you to take note of is we had lots of times where we had a whole bunch of 2's or a bunch of b's or 3's or whatever they happen to be. It's the term with the fewest of the same factor that limits how many factors appear in the GCF. So you'll notice on this one right here, we had 1x here and 2x's here. We were limited by this one that had the fewest. We had 4 2's here, but this one only had 2, so we were limited to 2 being common there. Same thing with the b's here, 2 b's here, 3 b's here, but it's the one with the fewest number of those factors that limits what we've got there. Okay, give the assignment 2.4 a try and see how you do. Thanks.